In the last chapter, we looked at least squares, regression, or prediction. What we're going to do now is look at a different form of prediction, and that's going to be when the thing you're predicting takes on a finite number of values, like, true or false. That's called classification, and we'll see how that works in this lecture, and we'll also see how to do it using least squares. So we'll start with what classification is. So basically, it's data fitting with an outcome that takes on typically non-numerical values like true or false, or spam or not spam, or dog, horse, or mouse. Right? These are examples. It could be different variations of a disease or something like that that you're trying to predict. Um, Now, in this case, the output values are called either labels. It's kind of obvious why it would be a label like a dog, that's a dog, or categories. And in fact, one way to talk about outcomes that are non-numerical or take on a finite number of values is to say that that's a categorical variable. Okay, and in this case, instead of you'd say data fitting, but basically what it's called is classification, is what you're trying to do. Now we're going to start with the simplest and frankly by far the most common case, which is so-called Boolean classification, and that just says there's two possible outcomes, and these could be, for example, true and false, or spam, not spam, or something like that, right? And so there, we're going to encode them numerically as +1 is going to represent a true for us, and false is going to be -1. Now, by the way, there are other encodings. A very common one is 1 is true and 0 is false. That's another very common numerical encoding of Boolean or truth values. And so the classifier is going to look like this. It's actually going to be a function. It's going to take in an n vector. Those are going to be our feature values. And instead of spitting out a number the way a prediction model does, what it's going to spit out is either -1 or +1. +1 means I think the outcome is true. -1 means I think the outcome is false. So that's kind of that's the idea. Okay. Now, there's a ton of applications of this. So I already hinted at one, email spam detection, right? So here, the way that might work is your feature vector X would contain features of an email message. It could encode word counts. It could encode the origin of that email and things like that. And those are just the features associated with that email. And then, of course, what we're trying to predict is that email spam or not spam? Okay, and we'd get a lot of data because if somebody clicks on spam, moves an email message to its spam folder, we can assume that she or he is considering it spam. Okay, if they don't, and we have some evidence that they actually read it, we can assume it is not spam. Okay, another one. This is a huge industry, is financial transaction fraud detection. So, for example, for a credit card. So here, what would happen is that X would contain features of the proposed transaction, like what are you buying? How much is it? What time is it? What's the store? All that kind of thing. And then also the initiator, so the person alleging that it's their credit card, right? And we'd get all sorts of things like, who are they? How old are they? What's their sex? Where do they live? All sorts of things. So all of that would be wrapped up together in one feature vector. And then your job is to look at all those features and to say, that's a fine transaction. Yep, that I think that's fine. Or you would say, I think that might be fraud. Now here, this is what people would call an imbalanced data set, meaning that, well, we hope that 99.9%, maybe more, of the transactions are actually valid, and a much smaller number are fraudulent. I make one minor comment. This usually works in practice. I can tell you actually how this works. So for fraud detection, a very common thing is a red, yellow, green. So it's actually three-way classification. And what happens is a transaction comes in. If it's green, it just it's accepted and the transaction goes through. If it's red, it's blocked immediately, right? Meaning it's reasonably confident that's not right. If it's yellow, that transaction is routed to a human being who looks at it and goes, "Oh, I see what's going on here. Yep, now I remember. Yep, she's traveling in Barcelona, and this okay, that's more than she would normally spend for a hotel, but it looks okay to me, right?" So, okay, back to our main story. Sorry. Document classification. So suppose I would just like to say, find me among these 25,000 documents, the ones, let's try to figure out, is it on politics or not? That'd be it. X could be a word count histogram in that case. Okay. Disease detection. So here X would contain patient features. It would include the results of medical tests. It would include symptoms, things like that. And then your job would be to say, does this patient have this specific disease? And then you would guess it. You'd make a guess. It also comes up in a digital communications receiver. So there, what happens is X, it's not called thought of a feature vector there, but it is actually, it's a received signal. It could be measurements of a received signal at different antennas or spaced in time. That would be the X. And then Y is a transmitted bit. It's either true or false, right? So, and then you would look at the received signal and try to guess if it's true or false. Now, typical ones in practice are going to have are going to be accurate like more than 99% of the time, which is good. So, okay. These are just applications of classifiers, which is just data fitting with a categorical label or outcome, right? And we're focusing for now on Boolean outcomes. Okay, now there's some interesting differences between this type of classification and predicting a number. So let's see what that is. If you have a data point, that's a pair, x, y. But remember, y is either like -1 or +1, meaning false or true. And then we have a predicted outcome. Y hat equals f hat of x. And it's just a function. We evaluate it. We either get +1 or -1. That's our prediction. Now, the way we measured errors in predicting an outcome that was a number was, like by the RMS value or the square, or it's just how far off were you? If it's 1 point, if the true value is 1.2 and we guess 1.3, we're off by 0.1. Here it's interesting because both the true value and the guess only take two values. Each of them only takes the value -1 or +1. Altogether, you've only got 4 possibilities. And so there's only 4 things that can happen in this case in a Boolean classifier. Let's see what they are. So one, we call that a true positive. Y, remember, is the actual value of the observed data. And this says that so true positive means it really was positive. And by the way, and we guessed it was positive. So positive is another way to guess, to say it's +1, okay? True negative, right? And true negative means it was -1, meaning you'd say that data sample is in the negative class or, whatever, has a negative label. And also, guess what? We guessed it. And so in these 2 cases, 2 of the 4 cases were right. This is a case where we guessed and we were right. Notice here it's actually kind of cool. We don't really expect in another prediction, if I'm predicting the temperature tomorrow at 1 p.m., I don't expect it to get it right to within, 4 digits, right? Not at all. But here, you're just right. I mean, you guessed it right. Now let's get to the 2 depressing cases. This is called a false positive. So false positive is this. It was really negative. The data point was really negative. That's what y equals -1 was. But we guessed it was positive. So basically we're saying, our model is saying, we think you have the disease. Now, the truth is you don't. By the way, the consequences of that, I think you can imagine, need not be good, right? Okay, so that's called a false positive. You can also have a false negative. That says it's actually positive, but we're guessing, we're like, yeah, you're fine, go home. Yeah, couldn't be better. Yeah, go ahead. So that's a false negative. That's also, obviously can have very bad consequences as well. A false positive, for example, in fraud detection means that you attempt to buy something or attempt to carry out a transaction and it's blocked, right? usually then you get something on your phone that texts you and says, hey, is this really you? Are you really trying to buy that, or something like that? False negative is interesting. That's when that's when a fraudster uses, actually studies your transaction. Well, I don't think they really do this, but it means that it's actually a fraudulent transaction, and the classifier is like, yeah, that's cool, yeah, whatever, sure, fine. That's a false negative. Okay, so obviously in the first two cases, the prediction is right, and then in the other two cases, it's wrong. Now, many different fields have names for these different things depending on the specific application. And I think another name for being right and wrong is, these are for the errors, right? One of these is referred to as a type 1 error, one is a type 2 error. I can't remember which is which. And so you just have to ask when you're in one of those situations, right? Like, what is type 2 error? Why can't you just say false negative, which seems to me clearer, but whatever, that's fine. Okay. Now, what happens is if I have a data set, and this could be a test set, or a training set, it doesn't make any difference. And I have a classifier. What it is I will calculate then for each of these x's, I will calculate y hat I, which is going to be f hat of x I, right? And so that's our guess. And so basically for each data point, we have two things. We have the true value of y, which is -1 or +1, and we have our guess, which is -1 or +1. And we divide all our data into these four different categories of the four possible things that can happen, and we put them in a matrix like this. And so, by the way, depending on the field you're in, you would either look at this matrix or a transpose of the matrix. And that even tells a lot about, whether you took, who knows, statistics or machine learning or whatever. Did you learn it in computer science or blah, blah, blah first? So, but nevertheless, this thing is called a confusion matrix, which I think is a wonderful term. So let's see what it is. It says you will actually count, that's the number of times. So n sub TP is true positives. It's the number of times in your data set that it was really true. That's what it means for y to be +1. And you guessed true, so you were right. Down here, that's true negative. So that's the number of times out of n, that's the total number of your data, total size of your data set. That is the number of times that it was really false. That's what it means to be in this second row. And you also guessed false, so you were right again. Now, the off-diagonal entries in this matrix are mistakes. They're errors. So these are the ones, that's false negatives. That's where it was positive, but you said, no, it's negative. And this is where here it was negative, but you said, yeah, it's positive. So these are wrong. So the off-diagonal, this whole thing together is called a confusion matrix, which I think is great. Because you would say things like, here you have confused class 1 for -1 or something like that, right? So your off-diagonal entries tell you about your confusion. By the way, if you had a diagonal confusion matrix, that'd be excellent. That means you never made a mistake. You nailed it. Okay, so the off-diagonal things are the bad ones. Those are mistakes. Diagonal ones are where you're right. Okay, now people derive tons of error metrics from a classifier applied to a data set. And I'll tell you the ones I think are the most clearest to me, but in fact, different fields use other names. I can't even remember what they mean like out of the specificity and whatever. Anyway, so you just have to ask. And once you integrate socially into a field or application area, then you'll realize, okay, everybody talks about these types of error rates, right? So okay, so here's one. This is super simple. It is the sum. It is the number of times you were wrong. That's this. That's this entry plus this entry. Those are your error rate divided by the total number. So that makes perfect sense. If that's 5%, it means that 5% of the time on this data set, your guess was wrong. That seems pretty clear to me. That is the so-called error rate. So people have the true positive or the recall rate. It's the number of true positives divided by the number of positives. So it's basically depending on the number of, every time when there's a positive, what's the fraction of them that you actually actually get them that way. And you would like that to be, well, 1 would be perfect. It would mean every time there was a true positive, you guessed so. False positive rate, that's another way to do it. That's the number of false positives divided by the number of negatives. So that's this. That's a false positive, remember, is when it's truly negative, right? But you guessed positive. So it just means among the ones where it's truly negative, how many times did you accidentally say, oh, it's positive? So that's it. Now, if anyone proposes a classifier, and by the way, we have not even mentioned one method of coming up with a classifier, but when we do, if someone says, here's my classifier, you're going to judge it by at least 1 and maybe 2 or 3 error rates, right? So you'd say, oh, that's a pretty good one. It's got a pretty high true positive rate, and a reasonably small false positive rate. Or, oh boy, my classifier has an error rate of 6%, but yours has an error rate of 12% or something like that. So this is the idea. And by the way, that's all done on a test set, because doing this on the training set is kind of meaningless, right? So, but at that point, it's a real thing. Like if you say my false positive rate is this and my false negative, and that's on test data, that's good. So let's look at an example. Here's a spam filter, and this is a test set. The test set has about 1,300 emails in it. And we can look at, this is the truth, right? If you look at the row, that's the actual truth. And we can see that, about 10% of the emails were spam, right? Because it's 127 versus 1,200. Okay, I mean, roughly 1,100. So, about 10% of the emails in this data set are spam. And then let's see how we did. Well, of the 127 that were really spam, we nailed it. On 95 of them, we said, that's spam, and we were right. Now, unfortunately, on 32 of the ones that were spam, we thought about it, and I'm anthropomorphizing the classifier. We thought that the classifier thought about it and said, no, it's not spam, but it was. Then we can look at the ones that are not spam. So there are 1,139 non-spam emails, and 1,120 times, that's a lot out of 1,139, we were like, that's not spam. But unfortunately, we classified 19 of those 1,100 emails that really were not spam. We classified them as spam. Okay, so these are our errors of the 2 different types, And so our error rate would be 19 plus 32. That's the total number of mistakes we made out of 1,266, and it's 4%. That would be one way to say it. One interesting thing about that calculation is it assumes that these 2 types of errors are equally bad. Actually, in a lot of cases, that's false, and we're going to come back to that later. But that's actually typically false, right? It could be that you care much more about one of these errors than the other. Okay, so if you want to know what's the false positive rate, it is out of the ones that were. So this is as among all the negative examples, of which there are 1,139. We falsely thought it was a positive in 19 cases. So we have a false positive rate of 1.67%. Okay, so this is just an example to show what a confusion matrix is, how do you interpret it, and so on, right? And if you want a single number, error rate is as good as anything else. But in fact, a lot of people would look at maybe 2 numbers